Hi, my name is dr.ahmath. Welcome to this lecture where we are going to discuss about the Newton's iteration. This is going to be our last lecture from the sequence of the lecture we are discussing about the applications of derivatives. So the Newton's iteration, it's a method which helps us to find the roots of functions or the zeros of the functions. So let's assume that a car dealer offers you a car for $18,000, and at the same time you can pay this amount differently by paying $375 every month. So obviously the car dealer is making some extra money out of this, and what I want is I would like to know what is the monthly interest of the car dealer if he's offering you to pay $375 every month within 5 years, right? Actually, you have to pay 60 months per $375, and I would like to know what is the monthly interest rate of this. So we can model all of this like interest rates, and we can get this kind of equation, which is going to be 48x times 1 plus x in the power of 60 minus 1 plus x in the power of 60 plus 1. And by finding the zero of this equation, I can find the interest rate, the monthly interest rate of the car dealer. So you see, so I know how to find the roots of the quadratic equation or maybe the cubic equation, but it is really difficult for us to find the roots of the equations, of the polynomials of the 4th power, 5th power, 6th power, and so on. And finding the root of the equation of the polynomial of the 61st degree, I think it is going to be difficult, or I think it is impossible to find this analytically. So what we want is we would like to find this numerically, approximately, and we can find the root of this equation approximately using so-called Newton's iteration. So I'm going to try to explain you the idea. So we are going to call the root of this kind of equation the point x, okay, the point x r, let's say, so that if I substitute this to the function, it is going to be equal to the 0. Okay, for example, if I'm given the x squared minus 4x plus 4 function, plus 4 function f of x, and I call the x to be equal to 2 as the root of this function, because if I substitute xr is equal to the 2 to this equation, it is going to be 4 minus 8 plus 4, which is equal to the 0. This is what I'm going to call as the root of the function. The root of the function, or the 0 of the function, it's the point on the x line, so that if I substitute this to the function, the curve is going to have the 0 height, or it's going to be simply 0. So let's try to learn what does it mean, the Newton's iteration. So this is going to be the curve of this function. What we want is we would like to find this point r on the x line. Because if I substitute this r into the equation of this curve, it is going to give me 0. Essentially, the curve, this blue curve, is having 0 height, or it is passing through the x-axis. So what I want is, I would like to approximate this. I would like to guess this. Okay, so I will choose any point on the x-axis, and I will say, hey, so this is going to be my guess for the root. So if I say, hey, if I give you 1 point on the x-axis, x1, and if I ask you, can you tell me whether this is the root or not? Well, how you would check this? So if I say, hey, x is equal to the 4 is the root of this curve or not, what you would do is you would just substitute this to here, right? And you would substitute this to here, 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 and check whether this is equal to the 0 or not, or check the height of this curve, right? So obviously, graphically, I see that the height of this curve is not equal to the 0 at the x1, right? So this is somewhere like it. So this point here has the coordinates x1 and f of x1, and obviously f of x1 is not equal to the 0, so that's why x1 is not the root. But this was our very first guess for the root. So what I want is I would like to improve my guess to find a root. And in order to do this, I'm going to create the tangent line to this curve f of x at this point x1, okay? And if I just draw the tangent line, it is going to be the line like this. And the intersection of this tangent line with the x curve is going to be my second guess for the root. You see, so in this case now, x2 becoming closer to the r, which I am looking for. So how to find x2 actually? So I'm going to write down the equation of the tangent line. If you remember, the equation of the tangent line is at this point, right? x1. So with the coordinates x1 and f of x1 can be found using this equation. Y minus f of x1 is equal to the f prime of x1 times the x minus x1 is the equation of this line. So what I have to do is I need to look for this point x2, right? Well, can you tell me what are the coordinates x and y coordinates of this point here at the x2, at the intersection point of this tangent line with the x-axis? The coordinates are x2 and 0 because the y coordinate is 0. So essentially, I'm going to substitute y to be equal to the 0 and x to be equal to the x2, right? Then if I just substitute this, I can find the following equation. It is going to be 0 minus f of x1 is equal to the f prime of x1 times the x2 minus x1. So what is unknown here in this equation is x2. So I have to find the x2 from here because I'm looking for that point. I'm looking for the second approximation of the root, right? So I can find x2, it is going to be x1 minus f of x1 divided to the f prime of x1. So this is going to be the second approximation. So, well, is it the root of this curve? Well, I don't know. So I think no, but how you would know this? So if you substitute x2 now into this curve, into this equation, and if it is equal to the 0, then this is going to be the root. If it is not, then this is not the root, right? So let's check this. If I substitute this, it is going to be this point. This point here is going to have the coordinates x2 and f of x2, which is obviously not equal to the 0. No, it is not the root. Neither. So what I'm going to do is I'm going to do this iteration one more time. So I'm going to create again the tangent line to this point, to this curve at this point. Then I'm going to take x3 as the intersection of this new tangent line with the x-axis. So analogously, as I did here to find x2, I'm going to find x3 using the same way. And obviously, you may guess that the x3 can be found using this equation, right? So the x3 is going to be x2 minus f of x2 divided to the f prime of x2. Then I'm going to do this procedure again and again. So I'm going to put this to here, then I'm going to create another tangent line and so on. You can see here that I'm approaching to the root as I'm keep doing these iterations, okay? So those iterations which helps me to find a root is called the Newton's iteration. And I'm going to write down the formula to find the iterations, like all the time the next term on my iteration. So the first guess, x1, is going to be any point on the x-axis. Then I'm just going to find x2, x3, x4, and so on, xn plus 1, just using this formula. Okay? At some point, I'm going to reach the root. How do I know whether I reached the root? So I'm just going to substitute the f at this point, xn plus 1, and check whether this is equal to the 0. Okay? So if you are given a problem where you have to find the root precisely, right, up to some digit after the comma, what you have to do is you need to check whether f of xn plus 1 minus the 0, because you would like to reach the 0, right? The distance between this point, the f of xn plus 1 and the 0 is smaller than some epsilon, or 10 in the power of minus 4, or some, and so on. So depending on up to which digit approximation, so up to which digit your approximation should be correct. Let's do a couple of examples, then we are going to come back to this. So let's say we are given this function, x cubed minus 2x minus 5, and we have to find its root. So starting approximation should be equal to 2. So x1 should be equal to 2. If you remember, we just need to use this equation in order to find x2 and x3. Okay, so I think we just need to find the second and third approximations. So in order to find x2 and x3, I need the derivative of this function, right? So the f of x in this case is going to be equal to the x cubed minus 2x minus 5. and f prime of x is going to be equal to the 3x in the square minus 2. Okay, then I'm just going to substitute this into this equation, and I will get the x2 can be found by substituting x1 minus, so x1 in the cube minus 2x1 minus 5 divided to the 3x squared 1 minus 2. Then I can find x cubed by just doing the same operation. So the x cubed is going to be equal to the x2 minus x2 and the cube minus 2x2 minus 5 divided to the 3x2 in the square minus 2, and so on. So this is how I'm going to find this. So I think I will give you a couple of equations here. So this is how we can find the approximations. So now what I want is I would like to find the square root of 2. Okay, so have you ever been curious to know what is the square root of 2? I assume that some of you know what is the square root of 2. Square root of 2 is like 1.4142, right? And you know this by just using the calculator, right? Just go take a calculator and press the square root of 2, and it gives you 1.4142. But the question is how your calculator calculates the square root of 2. Right? Obviously, it is also using some approximation methods. We can use, for example, the Newton's method to find this. So essentially, to finding the square root of 2 is the same as is equivalent with finding the root of the equation x squared minus 2, right? Because if you find this here, it's going to be x is equal to the square root of 2, right? So if you find the x here, so or the root of this function, it is the same as finding the square root of 2, right? X here is the square root of 2, the positive root of this function. And we are going to find the root of this function. So we are going to define what is the f of x. So the f of x is, in our case, is going to be simply x squared minus 2. The derivative of this f is going to be 2x, right? Simply, derivative is going to be 2x. So if I'm going to start with the approximation, let's say x1 is equal to the 3, then how I can find x2, x3, x4, and so on. I'm going to use this. I'm going to find them using this equation. Xn plus 1 is equal to the xn minus. What is f of xn? So if I substitute xn to here, it's going to be xn in the square minus 2. And what is the f prime of xn? So it is going to be 2xn. Right? So you just need to substitute x1 to be equal to the 3 to here in order to find x2. So let's try to do this together for this one. So the x2 is going to be equal to x1 minus x1 in the square minus 2 divided to the 2x1. So in this case, it's going to be 3 minus 9 minus 2 divided to the 6. It is equal to the 3 minus 7 over 6, which is roughly 1.8333. Okay? Then you can find the x3 using the same equation, x4 using the same equation, and so on. Okay? So what I'm going to do is I'm going to demonstrate the square root of 2 using the animations. So let's try to do this. Well, this is the animations created using the Wolfram Mathematica. So this is the CDF player, so you can play with this. So this is the equation of this curve, x squared minus 2. Y is equal to the x squared minus 2. So what I'm going to do is I'm going to choose the approximation here. So I've chosen here, the approximation here is going to be 3. You can see this as the black dot. So the next approximation is going to be the tangent line to this curve at this point. So I'm just going to choose the 2 from here. For example, this point is going to be here my next approximation. The next approximation you can see here on the top above the curve, there is an array with all of the approximation, which is 1.8333. If you remember from the slides, it was 1.8333, right? Okay, so our next approximation is going to be now this point, the intersection point, which is 1.8333. I'm going to find the tangent line to this curve again. So the second approximation is going to be 1.42612. The third approximation is going to be 1.41, and so on. So you can see here at the end, the numbers here on the array, so on the top of the array are not changing, right? So it means that we've reached the root already. Okay, so I'm going to show you a couple of examples of of demonstration of this method. So let us do this with the cosine of x. So let's say I would like to find one of the roots of the cosine of x. Okay, so I'm going to choose the x0. It means that you're changing the place of the first guess. Okay, then you can find the first approximation. You see, so I'm making the tangent line and I'm just finding the intersection of the tangent line with the x-axis. It is going to be the first approximation, the second approximation, third approximation, and so on. Okay, so you can start with this here, and you can see here how this method, iterational method, is approaching to the root. So, well, the number of the iterations you do in order to find a root obviously depends on how good your first guess is. So if your first guess is really good, is really close to the root, you can easily find a root in small number of the iterations. But if your first guess is far away from the root, it is going to be difficult. Sometimes it is even impossible to find a root if your first guess is bad. So when I say that your first guess is bad, is that you are going to choose your first guess at the extremum points. Here, for example. So do you remember what we call as an extremum point? The critical point, sorry. So the critical point is when essentially your curve, the tangent line, is going to be horizontal, which is going to never reach the x-axis, which is never intersect with the x-axis, right? You can see here that if your first guess is roughly equal to the pi, right, and the derivative of the cosine is sine, and the sine of pi is equal to the 0, right? Derivative of the cosine is equal to the 0. It means that the slope of the tangent line at this point is equal to the 0. It means that this tangent line is never going to intersect with the x-axis. If you remember, the intersection of the tangent line with the x-axis is going to be your next guess. Okay, so if your first guess is bad, so essentially it's one of the critical points, then you are never going to find the root. So you need to be careful with the first guess. So the first guess is the most important part to find the root using the Newton's iteration. So I think this is one of the really interesting examples of the applications of the derivatives to find the roots of any function. And this was the Newton's method. I hope that this was helpful for you.